Good morning, everyone. It's my pleasure to welcome Jason. Jason Cong is the Volgenau Chair for Engineering Excellence Professor and former Department Chair at the UCLA Computer Science Department, with joint appointment from the Electrical and Computer Engineering Department, the Director of Center for Domain-Specific Computing, and the Director of VLSI Architecture, Synthesis, and Technology, VAST Laboratory. Dr. Cong's research interests include novel architectures and compilation for customizable computing, synthesis of VLSI circuits and systems, and highly scalable algorithms. He has over 500 publications in these areas, including 16 Best Paper Awards and 3 papers inducted to the FPGA and Reconfigurable Computing Hall of Fame. He co-founded AutoSA, which developed the most widely used high-level synthesis tool for FPGAs, renamed to Vivado HLS after Xilinx acquisition, and more recently, Falcon Computing Solutions to enable FPGA acceleration in data centers, also acquired by Xilinx. He was elected to an IEEE Fellow in 2000, ACM Fellow in 2008, the National Academy of Engineering in 2017, and the National Academy of Inventors in 2020. He is the recipient of the 2022 IEEE Robert Noyce Medal. Welcome, Jason. It's my honor to invite you. Coming from Intel, getting Robert Noyce Medal, the latest recipient of Robert Noyce Medal adds a special welcome for you, Jason. Welcome.
Chitra, thank you so much for the introduction. So it's my pleasure to speak to this audience, and I always wanted to attend this events in person, but this is the second best thing that I can actually share some of my research results with you virtually. The topic today is democratizing IC designs and customized computing, and I'll explain what I mean in a moment. So the conference has a great theme talking about silicon catalyzing computing, communication, and cognitive convergence, right? However, if you look at the trend, the performance and the growth that of general purpose processor, which used to be the main engine that drives the computation, communication, the cognitive convergence, it had a spectacular growth in the 1980s all the way to 2000, but has slowed down considerably recently, down to 12% a year, and now down to 3% a year. And that's for the general purpose computer. However, we believe there's a lot of room where you can adapt the computer architecture to do domain-specific customization. So we actually submitted a proposal to the National Science Foundation in the US back in 2008, 2009. Unfortunately, we got funded, so we established a Center for Domain-Specific Computing. So the goal there was to look beyond parallelization to focus on domain-specific customization for significant power performance efficiency. The previous talk about a machine learning accelerator. That's a good example. I will also come back to that. And so we had a position paper 2011, and more recently we actually had a good overview paper about on our research in the past decade in IEEE proceedings. It's an invited paper, goes from single chip to data centers. So let me give you some successful examples of customization. The best known one probably is the Google TPUs, right? Everyone has heard about it. The first version was 2017. I'm just quoting the published result in 2017. That so it was actually an upgrade from DDR3 to DDR5, and the bandwidth goes up to 180 gigabytes per second. So at that time, and if you look at the data in the paper, that's 200x faster than general purpose CPUs, and even 70x that more performance, basically more energy efficient, right? Performance per watt compared to the at that time the leading edge GPUs. Of course, in the last 5-6 years, the both GPUs and CPUs has improved a lot, and the TPUs also went through multiple revision. But that was just a snapshot at that particular time. Nevertheless, you show the power of a customization. The problem, however, is that not everyone can do such a design because doing an ASIC design takes hundreds of millions of dollars, and from design process verification and all the way to creating mask. And also, it takes too long to build. Typically, a project like this takes somewhere at least 12 months, possibly all the way to 24 months. Often the time that the algorithm has changed, the application has changed. So what I'm going to say is that we want to enable everyone to be able to do customization. So what comes to our mind is to use FPGAs. Many of you probably are familiar with that. It stands for Field Programmable Gate Arrays. And really, because they have a lot of configurable logic blocks or lookup tables, you can customize it to implement any logic functions you want. In addition, that they also have a number of dedicated components, for example, memories, multipliers, I/O processors, right? So that give you the additional efficiency. If you have generated bit stream, you can reprogram the FPGA in seconds to get a new functionality. And also, it's very affordable. For example, you can go to the Amazon AWS cloud, spend $1 or $2 an hour, right, to get your FPGA and customize it to do high performance computation. All my classes are taught on Amazon cloud now using FPGAs just to do customization. So that's our main implementation platform. The shortcoming, of course, that the FPGA has a lower density and lower clock rate compared to ASIC designs. So you may lose 5x or 10x in overall performance. But nevertheless, I will show you that still there's a significant advantage compared to general purpose computing. So let me show you some examples. This is I'm taking, for example, sorting big data and terabytes of data or gigabytes of data as one example. We designed a multiple FPGA-based sorting engines. So let me tell you the one we have for a DRAM level sorting. So the first stage is that you all know about the merge sort. And we can actually implement merge sort in hardware where you can read data from a high bandwidth memory, HBMs. Typically, HBM has 32 channels, and you can, in our case, we pick 16 channels as input and another 16 as output. Then you recursively merge the data you have. That's the phase one. And you get a bigger and bigger chunk of the data which has been sorted. And then in phase two, we're actually going to reuse the merge trees we have in phase one and then merge this data together. So the result is that, to give you a kind of data point for comparison, we can sort 4 gigabytes of data in that 0.25 seconds. This is 85x speed up over the 32 thread CPU implementations. So even with FPGAs with customization, this circuit does nothing else except the sorting at a very high throughput. So you can still get tremendous improvement. The industry has used FPGA at a very large scale as well. So this is actually a case from Microsoft. In fact, in their case is that they have an FPGA configured as a bump in the wire before they connect to the data center switch, and they go through an FPGA. And so they can do a lot of on-the-fly computation. So this example they published was on acceleration for deep learning. And the paper was published again almost 5 years ago. You can see that with different devices, this is a different FPGAs from Intel, the Area 10 and the Stratix 10, and also different versions. And then also with different bit widths, you can go all the way to 90 teraops per second. If you remember my early slides, this is actually quite comparable to TPUs. But this one is totally reconfigurable. If you don't like the idea of using FPGA for deep learning acceleration anymore, you can reconfigure this to support search engines, data compression, or whatever applications you want. So that's the flexibility you have. So you may ask, hey, why that general purpose processor is so much behind this customized engine? Let me just show you one example. because general purpose processor, the keyword is general purpose, right? It's very powerful that I can implement any instructions you want. So they have this instruction execution pipeline. So think about it, if you just want to do add operation, right? You have to fetch the instruction, right? And you do a decode to see which instruction is that. And then sometimes to avoid the name conflict, you have to rename one of the operands or both operands. And then maybe the data is not available, so you actually have to wait, right, to be scheduled in a reservation station. And finally, when both data available, you execute in the ALUs, and then finally you can write it back. But if you are doing out of order execution, you have to have a reorder buffer so that everyone before you has been committed and you can write it back. So you can see for a single add operation, just two numbers, you get a sum, you go through this lengthy process pipeline. So we quantified it in our paper in Design Automation Conference back 2014, saying that there's really in this long pipeline, there's only 10% to 30% of a computation is useful. The rest is the tax you pay to support general purpose computation. In fact, this paper from Stanford also make a further point, saying that the specialization or customization can allow you to have special data type and operations. So in one cycle, you can do tens or that to 1,000 instructions, equivalent instructions, so give you this much of a gain. It's a massive parallelism and 1,000x or more, not 16x or 32x. It is the number of cores you have. And then it also has customized memory, right? High bandwidth, low energy usage, and also reduced or amortized overhead. For example, as I said, you don't have this long instruction decoding pipeline. And then you also can do algorithm architecture co-design, which we have done quite a bit in the past as well for various kind of application. So altogether, that's where you get this 10,000x energy efficiency. You can get this on ASIC. You can still get it on FPGAs even with 5x, 10x of a loss of efficiency, right, relative to ASIC, but still tremendous gain over customized. Go for general purpose processors. So you may say, okay, great. Then what's the problem? That why not everyone designing own customized accelerators? The problem is that most of the people that in the IT industry are software developers. For example, I'm taking the data from United States. There are about 1.8 million software developers. And this is from the US Bureau of Labor Statistics. There are only about 66,000 people that they consider computer hardware engineering. Whether they can all do IC designs or FPGA design, I'm not sure, but all the hardware designers are in the 60s. So the difference is that almost 20x, 30x, or even larger, right? So basically, the FPGA and ASIC are not easy to design. Not everyone can do that. So that's actually the theme of my research. Is I want to enable every software developers or most of the software developers to be able to design customized computing engines. You may say, is it really that hard? I heard this thing called the high-level synthesis, where you can take the C programs and then generate accelerators. Indeed, there's tremendous progress on this subject in the past. In fact, my lab is at the very forefront of that. Some of you may read in our paper back in 2006. We have a high-level synthesis system called XPilot. It was quite successful. We can synthesize something like an MPEG decoder automatically, and then we get a lot of industry interest from the industry. We spin up a company called AutoPilot, and was a product called AutoPilot. The name of the company called AutoSA. That's got acquired by Xilinx. Chitra mentioned it in the introduction. So that's the basis of their Vivado HRS high-level synthesis tool. It allows you to do a C-based synthesis. We support IEEE standard floating point operations. There's a lot of special optimizations we have. The quality of the result matches or exceeds the RTL designs in many cases. And so if you are interested in all the detail, we have an invited paper, a keynote paper in the IEEE transactional CAD, now more than 10 years ago. There's a high-level synthesis for FPGA from prototype to deployment. If you do a Google search, there are thousands of papers using Vivado HRS. I'm sure some of you in the audience probably have used it quite a bit. You said, that's great. Isn't that the case? A software designer can just use this tool to create accelerators, but not as quite as simple. Let's take a very simple example, like a CNN, convolutional neural network. You are very familiar with that. With some initialization, the main computation is the 6-level nested loop. Basically, for every output image, you're going to do convolution on every input image, and you do it for the row and the column, and you do this P times Q convolution, right? The K by K convolution. The good news is that you just feed this C code into that high-level synthesis tool. You do get a circuit, but the circuit actually is 80x slower than even a single core CPU. So you don't get acceleration, that you get actually deacceleration. So what happened? The problem are multiple. For example, you take these parameters, you map it to the this DRAMs, and then you are reading it at a 32-bit at a time. And also in CPUs, you have cache, you cache the data, but this time that by default, when you design your own accelerator, unless you specify that there's no cache, there's no data reuse, you have to get it from DRAM every time. Also, if you don't do anything, there's no parallelization, that all these loops are executed sequentially. Plus, there's actually memory bank conflicts that although there's plenty of on-chip memories, you cannot utilize that very efficiently. Also remember FPGA, the clock frequency typically is 5x slower. So this runs at 300 megahertz versus CPU can run at 2 gigahertz, right? So as a result, you actually are slower than a single core CPU. Of course, like my students, they get this result, they will not be satisfied, they will optimize. So they will introduce on-chip buffers, right, to cache the data. They will do fine-grained pipelining. They will do fine-grained parallelization. They also do coarse-grained pipeline so that you can overlap computation with communication. And then you will do a lot of memory partition so that you can have a huge amount of concurrency, like what I was shown in the early slides. So with this optimization, now we are get 7,000x speed up over a single CPU core. Even you have 32 cores running or concurrently, we are still at let's say 20x at the 30x faster, right? But it's a lot of effort. You can see that 6 lines of a code become 150 lines of a code with 28 pragmas, tells you where to do memory partitioning, how you do pipelining, and so on and so forth. This is where most of the software developers stop. They kind of get worried whether I can handle that. So, so this is actually the problem we want to overcome. We want the software programmer to start with the language they're familiar with. For example, Caffe, TensorFlow, Spark, Playwright, or whatever domain-specific language, or at least they can start from C, C++, without much of a modification. And so we actually have support of this kind. And then internally, we're going to compile it into some intermediate representation. So we have this HyperCL, which a joint work with Cornell that won the best paper award at PGA 3 years ago. And the MLIR is a community-wide effort originally started by Google and Intel. So, and from here, then we're going to create automatically customized architectures, for example, systolic arrays and stencil computation. There's also a new type of architecture we call that composable parallel and pipeline architecture, or CPP. So if you have a certain patterns, we will generate this automatically for you. If you don't, we're going to use machine learning techniques to actually search for best optimization. So as a programmer, as a designer, you don't have anything. You just write efficient CPU-friendly code, and then we can give you the customized hardware. So that's what I call democratize, like customized computing or democratized accelerator design. So most of the IT professionals can enjoy that. So I'll give you two examples. One is this architecture guided designs. Uh, Many of you have heard this concept for the systolic array. So we want to be able to design that automatically. So the concept of systolic array is very elegant. So you have a set of processing elements or PEs. They are connected in 1D or 2D grid. And they give you a massive parallelism. Obviously, all of them will be doing some executions simultaneously. Moreover, they give you a locality. Each processing elements only communicate with its neighbors, either in the horizontal direction or in the vertical direction. So the locality gives you the energy efficiency. So that's why it's so popular. For example, Google TPU uses solid array, Tesla self-driving cars. They have some accelerator based on the systolic array. Also, the Amazon, they are influencing Android. However, that it's not easy to design a systolic array. I can warn you that. Let me tell you the story. We started this effort back in 2014. Without knowing actually Google's effort, we independently designed a systolic array for matrix multiplication. I have a very bright undergraduate student and worked with me for actually 5 months in the summer and the summer plus the 4th quarter. And we wrote the 1,700 lines of RTL code. And finally, we did get it running at close to 200 gigaflops per second on the Xilinx FPGA. This is considered state of the art. You may say, well, student may not be that efficient, but you look at this data coming from Intel. It's very similar story that, in fact, that this design per HMN, BGG16, and then matrix multiplication, they are all systolic designs. They go from 4 months all the way to 18 months, right? So it shows you the time to do coding, verification, performance tuning. So that's actually the kind of a hurdle, the barrier that we're facing. We want to automate this process. And the way we do that is that now we have a completely automated tool. You can actually give me the C code that actually we're going to rely on polyhedral compilation module to do a legality check. First, we want to understand whether your loop or nested loop is feasible to be implemented by systolic array. The way we check that is to make sure there's a uniform, constant dependency of distance 1, right? And then if it can be done, then we'll do computation management, communication management. We can actually have an auto tuner to look for the best configurations. And then finally, we can give you systolic array either in Xilinx FPGA or in Intel FPGA or in ASIC through this mentor Catalyzing C. So let me give you one example why it's so difficult and what are the solution space we are facing. So first, you have this concept called the space-time mapping. So this is just a 3-level nested loop for matrix multiplication. We are all familiar with saying that I for all I or j, and basically for each ij elements, I'm going to do this aik times bkj, right? The summation of that over all k. So for this three-level nested loop, you have to decide which levels goes to the space dimension, which level goes to the time dimension. So that's called the space-time mapping. So in this case, I'm taking ij into the basically space dimension. The k will be executed sequentially on each PE. That's the time dimension. But you can have a huge matrix multiplication. It's too big to map to a single systolic array. So in this case, you got to tile. Maybe you can say my systolic array is small. I can only design a 4x4 systolic array. So that's why I have to tile my loop. So the innermost 3 levels nested loop is 4x4x4. So that's called array partition. You go from a arbitrary design to a kind of a physical implementation. And it's often the case that the computation may take more than 1 cycle, and for the innermost loop, it's not that ideal. I do 1 cycle of communication, I hand it a computation, hand it to my laborers. So what happens if you do 6, 8, or 12 computation? So in this case, while I'm doing finish one, I'm going to pick up another independent task. I'm going to execute it. That's called the latency hiding. So basically, I'm going to take some further loops that I'm actually doing that in a pipeline fashion at the innermost loop. And then finally, I will actually do the SIMD vectorization. The PE doesn't have to be executing just one element. I can execute multiple elements, right? The vectorization. So, so these will be all done automatically. Of course, you say, how do you decide the parameter? What's the tiling parameter? What's the vectorization parameter, and so on and so forth. So for this, we have a intelligent search engine where we do mathematical programming-based optimization to start with, and we do evolution-based search. And as a result, that we have a highly optimized solution. You can see, for example, for matrix multiplication for CNN, the only number of input lines is somewhere from 7 to 10, right? The C code, you consider the loop nest. And the output high-level synthesis code are in close to 10,000 for each one of them. So this shows you the productivity gain. Not only that it's highly productive, that we also can generate highly competitive designs. For example, I'm showing you the comparison in the AutoSA in our solution compared to the reference design state of art in other applications. We are consistently better in both the performance and also very comparable in the DSP efficiency. Right? So this tool is completely open source, and if you are interested in it, you can go to my my lab's website and download it and play with it. And we'll be very interested to hear your feedback. If you like it, you should give it a start. Now you can say, well, that's wonderful. For Systolic array, we understand you can cover that very well. What about the general C++ program? Maybe I want to do some data compression and encryption. Can you generate the computing engine very efficiently? So for this, we also made tremendous progress. The way we have that is that first we build on this Merlin compiler developed by Falcon Computing. That was acquired by Xilinx, but it's an open source project. So many of you know OpenMP for do parallel computation. So this is just a very OpenMP style. Remember in OpenMP, you write a program like a Pragma OMP parallel. You talk about how many threads you use. Here's the same thing. You can just say Pragma Excel. I want to do acceleration parallel. How many parallel engines I'm going to create, right? So, and inside the compiler, they will do automatically on-chip memory banking, partitioning, external memory busting, streaming, and also the interface with OpenCL and so on and so forth. So this has been very effective. For example, for this OpenCV library, used to be the case, manual high-level synthesis design, you have to put in 20-some parameters per design, right? Plus 50-some designs in the library. Merlin only need about 1 or 2 parameters. And not only that, so that's reduction on parameters 15x. I use it in my class, and I can see that the Pragma reduction from 27 to 9. Moreover, that the performance also improved by 4.3x. So in fact, I just organized the workshop. There's a quite a big discussion about Merlin compiler. Again, it's open source now. Thanks for Xilinx support. You can build things on top of that. So what we have is actually to build things that are on top of this. The goal is that even not 1 or 2 parameters, we want to have 0 parameters. So the way we have is that, for example, you look at one of this polybench example to do basically double matrix vector multiplication. Code is like this. You can just give it to high-level synthesis to get a solution, but I bet the quality will not be very good. With Merlin, actually, it's quite clever that you can just add 3 parameters. One is a pipeline, the other one is parallelization, and then the other one is parallelization with reduction. So that you get 122x speed up. So this is the optimized code. If you have some good hardware design intuition, so this parameters are reasonable because it's not that too many. Now our goal is to remove this completely. And you can say, how do you do that? Of course, we want to give it to a machine learning algorithm. Machine learning algorithm doesn't know where to put it in, where not to put it in. It will start with all the possible candidates, right? And then we will use a deep learning model to find out the best one. So you give me this C++ code, we're going to Merlin compiler, and then we're going to get one solution, and then we're going to analyze the solution, just as you, for example, look at the VTune or other profiling result. We know where is the bottleneck, and then we're going to, for that loop, we're going to pipeline or unroll, and we're going to iterate. And also we may actually create some local perturbation. So we can get a number of designs. So that's actually how we generate the training database. We have to train a machine learning agent, right, to do how to do that. And we do it not only for one application, we do it for a whole bunch of applications. And so now the second time you give me a new design, right? I'm going to actually go through LLVM compiler. This is a very popular compiler, that intermediate representation. From there, I get a graph, because it's very difficult for machine learning algorithm just to understand your program text. Once you get a graph, we call that the CDFG, control data flow diagram. So it tells that how data is going to flow this graph, what kind of computation you do at every node, what's the dependency. This gives a lot of information to a machine learning agent. And from here, actually now we're going to create a graph neural networks. And first we do the encoding part. So this is the way you do graph encoding. So each node has a feature, and you're going to compute a new feature iteratively based on your neighbors. For example, this node 1, neighbors 2, 4, and 3, you do a weighted sum of their features, and the weight is learnable. And then after that, you do a transformation of the features from, for example, from 3 vectors to 3 elements vector to 4 elements vector. And this matrix can also be learned. It's quite similar to the case with deep learning for images. And eventually that we add all of this together, we get a graph embedding that represents the program. From there, we have an NLP prediction layers for area, delay, and so on and so forth. So this is actually the model we have. Let me just show you some result. So this is GNN stands for Graph Neural Network. DSE stands for Design Space Exploration. You can see in terms of latency prediction, DSP, these are the resources, lookup table, flip-flops, memory. So we are all very accurate compared to other methods. Right? And also you can see the benefit as you add more examples. This is all normalized to the initial configuration. We get more and more accurate. In fact, this result can be generalized. We could have transfer learning. So for example, we train this on 15 designs and with hundreds of or thousands of configurations. You give me a new design. Actually, in this case, we tried 4 more new designs. And we actually can find these parameters. And compared to other kind of heuristic search, we can be somewhere 11x faster to all the way to 80x faster with comparable result. Used to be the case, you have to run 24 hours for one design, you can run less than 1 hour. So we are very encouraged by this success. The key message is that the program we start with has absolutely no parameters. It's just a program very familiar, very friendly to software programmers. So with the time constraint, I think I will now talk about the other effort, but we have many other things going on. For example, we can take from TensorFlow to FPGA for deep learning, acceleration, and the previous talk also mentioned about this kind of accelerators. You may actually have application deal with graph-based applications or other task parallel applications. So we have a package called Tata. We can support legacy code. By the way, for a high-level synthesis to work, you cannot have pointers, you cannot have recursions. But now we can get transforming programs into this kind of a clean form more or less automatically. You also need to do performance debugging. When you don't get the performance you want to know, hey, where do I focus? So we have papers on this. And we can integrate this into near storage acceleration, and we can improve the clock frequency that with kind of automatic interconnect pipelining. And more recently, is that we can use this HRS-based methodology to reduce physical design time by massive parallelization to decouple the computation of each step. So all of this and can take us another a few hours to go through. So, but I will stop here. You're more than welcome to go to the website of my lab to get more details. So this is the final message I'd like to get. You may remember the Turing Award lecture by Hennessy and Patterson back in 2008. They are saying we're in a new golden age for computer architecture. What I want to say is that we want every programmer, not just the architects, to participate in this golden age. And you can build your own customized accelerators, for example, on field programmable fabrics. And if you have more money, for sure, you can use the same methodology to build it on ASICs. And this is either on-premise in your own data centers and or in a cloud. And I hope many of you will join this effort. And I hope our tools can help you to achieve this kind of goals. With that, I want to thank the funding agencies, National Science Foundation, CRISP Center, and our CDSC industry partners who have a very active partnership program with industries who are interested. We'd be glad to talk to you. Intel is a member, Samsung is a member, and Qualcomm and many others. So we hope more can join and work with us. And of course, all of these, this result is only possible with a multi-year dedicated effort from students, postdocs, and many collaborators. Thank you for your attention. I'll be happy to take questions.
Thank you very much, Jason. It was an excellent talk and great insights, Jason. The numbers are amazing and amazing. That's all I can say. All the speed numbers that you mentioned, all the execution numbers that you mentioned are extremely good, Jason. Thank you so much for this. I have only one question, Jason. There is a question about, will these methodologies be extended for ultra low power applications? That's the question.
So the ultra low power can come in in multiple ways, right? One is at the device level, right, at the circuit level. So now our emphasis with these tools, obviously, is at the architecture level. By this customization, and if you don't have to go through its general purpose pipeline, we easily see 10x, 100x in the energy efficiency improvement, power reductions. And so you don't get rid of all this extra logic, which you don't need, right? So you just focus on. Also, there's an opportunity for algorithm architecture co-design. For example, we can take the arbitrary bit width to come down, to hardware acceleration. Take the machine learning as an example. You can reduce the bit width, right? It's a trivial, go from 16-bit to 8 bits to 4 bits, sometimes in 2 bits. So that's one. Another trick we play is that maybe you can have more bits, but in each number you have, you only have one non-zero bit. For example, I have 8-bit numbers, right? So that can be either, depends where is this one, and you get a different one. So then this can be done very efficiently through shift instead of multiplication, right? So if you can change your algorithm this way, then you can really get a very efficient hardware implementation together with the algorithm innovation. So for that, for example, this particular work, we had the paper with the best paper award in low power symposium, ISLPB, I think it's 2019, you can look it up. That's an example for the bit sparse architecture.
It's our honor to have you here, Jason. Thank you so much.
My pleasure.
Thank you so much, Jason.